Alright, today's lesson is on 6.1, which is the exponential function and its inverse. Alright, as I said before, today's lesson that I'm doing is 6.1, the exponential function and its inverse. And the goals of this lesson are, you know how to plot exponential functions in the form of y is equal to b to the power of x, and its inverse function, which is simply just switching the variables. And you can determine the rate of change of an exponential function. You're also able to determine the y-intercept of an exponential function and the x-intercept of an inverse exponential function, and determine the domain and range of both exponential and inverse functions. And for review, there's two websites I've given in case the review I provide isn't enough. And what you basically need to know is that an x-intercept is a point on the graph that crosses the x-axis. In order to obtain the x-intercept, you have to make y equal 0. So for instance, for this scenario, you have to input 0 as your y, and then your output is 1, because anything to the power of 0 is 1. Okay, so that's why you get 1 and 0. This is your x, that's your y. In order to obtain the y-intercept, you have to make x equal 0 and evaluate for y. So you input 0 here, anything to the power of 0 is 1. So therefore the y-intercept is 0 to 1. And that's your x, that's your y. So key points, you have to remember these two factors and understand that to find an x-intercept, you make y equal 0. To find the y-intercept, you make x equals 0. And the asymptote is a line, which is this dotted line, or curve, which a function approaches, but it'll never cross or touch this dotted line. And for this case, it's y is equal to 0, and the vertical asymptote here is x is equal to 0. So this dotted line, this function will never ever touch or cross that, even though it looks like it, but it won't. Okay, so update video. Ms. Nguyen said I had to explain the exponent laws. So the first law is that anything to the power of 0 equals 1. So here's a big number to the power of 0 equals 1. And if you have the same bases, and you could just simply add the exponents. So for example, over here it says 2 to the power of 3 times 2 to the power of 5. You would just simply write 2 and then just add the exponents, which are 3 and 5. So 3 plus 5 equals 8. So your answer would be 2 to the power of 8. And if you have an exponent on top of your base and then an exponent outside the brackets, you simply just have to multiply both exponents. And an example of this is 2 to the power of 3 bracket exponent 5. Instead of manually doing this by hand, you could just simply multiply the exponents. So 3 times 5 is 15, right? So your answer would be 2 to the power of 15. And if you have of the same base over a division sign, you would simply just subtract the top exponent by the bottom exponent and a minus b. So the example here is that since the 2 to the power of 5 is on top of the division sign, you'd simply just subtract the 5 minus 3 and you get 2 to the power of 2. And similar example here, you have 2 to the power of 3 over 2 to the power of 5, which is equal to 2 to the power of negative 2, because 3 minus 5 equals negative 2. And if you want to convert this back to this kind of form instead of a fraction form, all you have to do is turn the a into a negative a, and it'll become like this. So for example here, we have 1 over 2 to the power of 3, right? Well, if you were to change that to 2 to the power of negative 3, if you were to rewrite 2 to the power of negative 3, it's just flipping this number to 1 over 2 to the power of 3. And then the final one is x to the power of a over b. And this is simply saying the root of something, and then the a is just put inside the bracket or outside the bracket. So an example here is that 4 to the power of 1 over 2 is just simply saying the square root, meaning what two numbers multiply to 4, and then you would just exponent to 1. And the other example here is 5 to the power of 4 over 2. So you put the root sign, and then it's a 2 here, and then you would power this to 4. So you'd find the root 5 using your calculator, and then you would multiply it 4 times. And these exponent laws, as I said before, you do have to memorize them. And once you know them, you'll just need to apply them. All right, the rules that apply for both exponential and inverse functions, these are the key concepts that you're gonna learn this unit. And basically, both functions must have a b greater than 0, and b cannot equal 1. And the reason for that is, well, you put 0 in, it's a pointless function if you put b as 0. So that's not beneficial anyways. And if your b is equal to 1, anything to the power of 1 is just 1. So you're just gonna have like another pointless function. So that means b has to be greater than 1. Well, if b is greater than 1, then the function has an exponential growth, or in other words, it's increasing. And, okay, that's a bad representation, but you get the idea. This is increasing. And if b is less than 1 but greater than 0, then the function has an exponential decay, or it's decreasing. So like it's going like that, and this is like decreasing, right? Because if this is increasing, that's decreasing. Because as x increases, y is increasing, so it's increasing. As x increases, y is decreasing, so it's decreasing. An example of a function with a b that's greater than 1 and that is increasing is the exponential function y is equal to 5 to the power of x. And since b is greater than 1, this function is increasing. Similarly, the inverse is x is equal to 5 to the power of y. And b is greater than 1, so this one is increasing as well, but it's an inverse. And an example of a function that has a b less than 0 but greater than 1 is y is equal to 1 over 5 to the power of x. Since this is a decimal that's less than 0 but greater than 1, the function is decreasing, and the inverse would also decrease as well, because b doesn't change. It's still 1 over 5, 1 over 5. The only difference is the y and x. All right, rules that only apply for exponential functions are an exponential function is written in the form of y is equal to b to the power of x. And all exponential functions have a y-intercept of 1. So if you remember, a y-intercept is when you input 0 into x. So b to the 0, right, is just 1, because anything to the power of 0 is 1. So your output is y is equal to 1 when x is 0. So x is 0, y is 1. And all exponential functions have a horizontal asymptote at y is equal to 0. Now, as I said before, y equals to 0 is just simply this line, and the graph will never reach that line. It'll never cross 0. Okay? And here are some examples. So an example of a function that's, well, an exponential function is y is equal to 2 to the power of x. So it's exponential function because y is here and x is there. And if you think about it, x is your input, right? So x can be anything you desire, but y has to be greater than 0 because you can't get 0 no matter what input you put as x, because b to the power of 0 is 1, and then b to a decimal or a negative number is just going to give it a small number that's a decimal, but it will never cross this 0 line here, okay? And since b is greater than 1, the function is increasing. Similarly, y is equal to 1 over 2x, right? So it's decreasing since b is less than 0 but greater than 1. It's an exponential function. X can once again equal everything, and similarly y has to be greater than 0 and y can equal everything, but everything above 0. And here are the examples that I've given. So this function is y is equal to 2 to the power of x, and as you can see, it's increasing, and there's an asymptote of y is equal to 0, and this graph will never cross it, even though it looks like it, but if you were to zoom in on Desmos, you could tell that it's not ever going to cross this line. Similarly, y is equal to 1 over 2 to the power of x is decreasing, and it'll never cross y is equal to 0. And yeah. All right, the rules that only apply for inverse functions are, well, the first one is an inverse function is simply just, if this is the exponential function, the inverse of it is just switching the variables. So y is equal to b to the power of x. Instead, the x comes down there and the y goes up there. And all inverse functions have an x-intercept at at 1. So if we're talking, this is the inverse function, remember? So in order to find an x-intercept, y has to equal 0. So if you put 0 in, x is equal to b to the power of 0, anything to the power of 0 is 1. And if this is x, that's y. The statement's true. So the x-intercept is at 1. And if the inverse function, x is equal to b to the power of y, has b greater than 1, then it is increasing because b is greater than 1. And there's a reflection of y is equal to b to the power of x over the line of y is equal to x. So it'll look something like this. This is y is equal to x. So they'll both reflect off each other, and you'll see it later on. And if the inverse function has a b less than 1 but greater than 0, then it is decreasing, because as I said before, b is less than 1 but greater than 0. And ignore this part, this was a mistake. But both x is equal to b to the power of y and y is equal to b to the power of x and x equals b to the power of y will reflect each other over the line of y is equal to x. And you'll see that later. So the easiest way to plot an inverse function and to plot its exponential function is simply finding the coordinates on the parent function, meaning the exponential function, which is y is equal to b to the power of x, and then you switch the x and y values for the inverse function, and then you plot it. So let's just say, for instance, your parent function is y is equal, so 6 is equal to b to 3. So I don't know what this b is, but we'll just say this is what happens. So you put b to the power of 3 and you get 6 as your output. So your coordinates are 3 to 6, right? The inverse of it would just simply be switching the points. So 6 would become your x, your new x, and then 3 would become your new y. And if you were to do the entire graph, they will reflect upon the line of y is equal to x. So an example of the function that I've given is x is equal to 2 to the power of y. Once again, this time it's different, however, for the domain and range because your input is y, right? So y can be anything you desire, but x has to be greater than 0 because there's no way you're going to make this side equal 0. So x has to be greater than 0 and x is equal to everything, and y is equal to everything in range. But here b is greater than 0, right? So b is greater than 1, right? So it's increasing, and then here b is less than 1 but greater than 0, so it's decreasing. And this was supposed to be red, but I ain't got color ink at home because I'm broke. So b is greater than 1, right? So this is increasing because as x increases, the y is increasing as well. So this is an increasing function. And for this one, x is equal to 1 over 2y. b is less than 1 but greater than 0, so it's decreasing though because as x increases, y is decreasing. Okay, so to show everything I said in pictures, basically here's y is equal to 2 to the power of x, which is the exponential function. I'll just abbreviate it as exponential, xp. And then this is the inverse of it. So x is equal to 2 to the power of y, right? So as you can see, as my input is 0, okay, this would be like above it, but once again, I'm broke, so yeah. So 2 to the 0 is 1. So same thing here, 2 to the power of 1 is 2, right? Now, if you didn't want to do all this gibberish, simply just switch the points around, and then you plot it. And it's plotted here, but Desmos it's zoomed out, right? So, but I wanted you guys to see that it reflects, but yeah, you could just flip it and you're good. But if you wanted to prove it to yourself, because like you want to understand it, then once you flip it, right, you put this in. Your input is y now for the inverse, so 2 to the power of 0 is 1. So x is equal to 1, y is 0. 2 to the power of 1, x is equal to 2 now, because yeah, 2 to the power of 1 is 2. So it works. So this is your y is equal to 2 to the power of x. And this one is for that one, the inverse of it, the inverse of this. And this line over here, this line over here is y is equal to x, right? So this is like a perfect mirror of that, and all inverse functions are mirrors of their parent function. And I think I forgot to state that for this one, and I only said it for this, but it doesn't matter. The point is, if you have a function and you find the inverse of it and you plot it, they're always mirrors of each other above the line of y is equal to x. So if you want to write that down, because I think I forgot to say that, but they are always reflections of each other. If you find the inverse of this, you're going to get that again. You find the inverse of that, you get this, okay? And y is equal to x, you get that. And for this one, this is a b less than 1 but greater than 0, and this one here is b is less than 1 but greater than 0. And okay, what this exponent stuff, okay. So this should be above, right? But I didn't have the money, so power to the power of x. So 1 over 2 to the power of 0 is 1. 1 over 2 to the power of 1 is 1 over 2, or 0.5. And the inverse function of this is that, because you just switched the variables, right? Hold on, making it ugly. So if you're once again, too lazy to do this part, too much work, why waste time? Just switch the coordinates around, right? So this becomes your y, that becomes your x. This becomes your y, that becomes your x, right? And then if you want to prove it to yourself, you could plug it in and it'll work. It works. And, oh yeah, I forgot. So y is equal to 0 here, remember that. And for here, x is equal, for this function, x is equal to 0. Because you remember that your y cannot equal 0 for your exponential function. And then for this, y can equal everything, but your x cannot be less than 0, and it can't be 0 either. So you have an asymptote here of x is equal to 0, and then for this function, y is equal to 0. Similarly, for this one, y cannot equal 0, so there's an asymptote of y is equal to 0. And then for this one, your x is your output, right? So x cannot be 0 or less than that, so you have an x is equal to 0 asymptote. Okay? And then if you look at it carefully, this one does mirror that over the y is equal to x, because as I said before, if you have a function and you find the inverse of it, there will always be mirror images of each other over this line of y is equal to x. Okay, so if you look at it diagonally, like flip your paper around, you kind of see that this does flip upon that and that does flip upon that. And so they are mirror images of each other, which means they are inverses. And yeah, we're going to move on to the examples now. All right, so for this example, consider the function y is equal to 3 to the power of x. So for the key features, we know that b is greater than 1, right? So if b is greater than 1, then it's an increasing function, as I said before in the lesson. So, right, increasing function. And also, you know that, okay, so we know that y is equal to 3 to the power of x is, well, since b is greater than 1, the function is going from quadrant 2 to quadrant 1, which is what q2 represents quadrant 2, q1 represents quadrant 1. And the domain and range of the function is that d represents domain, right? And domain is your x input. So x is like what you desire, so x can be any input that you like. So we can say x is equal to all in range. However, the range is what our limitation factor is. So since our b is greater than 1, there's a horizontal asymptote of y is equal to 0. So that would mean the graph will never cross 0, right? And since it's always in quadrant 2 to quadrant 1, that means our range is y has to be greater than 0, and y is equal to all in range. And for C, what is the y-intercept? Okay, in order to find our y-intercept, you have to input x as 0, right? So when you input 0 as your x value, 3 to the power of 0 is 1. So your y is equal to 1, which therefore means your x-intercept is 0 and 1. And yeah, and then in order to find your x-intercept, you have to make y equal 0. And when you make y 0, there's no x input that you can get to make this as 0. So anything you input as x won't make this equal 0. So that means there is no x-intercept. Now, in order to do E and F, to identify what are the intervals for which the function is positive and or negative, you just have to look at your b. So since our b is greater than 1, that means the function is in the positive quadrants, meaning in quadrant 2 and 1, because these two are positive, but these two quadrants are negative. So since b is greater than 1, this function is always positive. And for f, it says what are the intervals for which the function is increasing and or decreasing. So as I said before, all we have to do is look at our b value, and since our b is greater than 1, this function is always increasing since it's going like this. It's never going to. So for f, this function is always increasing, and your intervals would just be x is equal to r for both, because no matter what you input as x, your function is always going to be positive. No matter what you input as your x, the function is always going to be increasing. Like table of values. So here I have my function y is equal to 3 to the power of x. And as my inputs, I chose -2, 0, 2, and 1. So if you were to input 3 to the power of 2 negative in your calculator, 3 to the power of 2 negative would be 0.111111. And that's just the same thing as 3 to the power of -2. But if you're too lazy, if you want to apply your exponent laws, you simply insert -2 as your x value. And since, as our exponent law said before, you have to flip this. Since it's over 1, you flip it, and you get 1 over 3. But then the exponent is applied to both, but 1 to the power of 2 is just 1. So you don't need that there. And 3 to the power of 2 is just 9, because 3 times 3 is 9. So our coordinate is 1 over 9, or 0.11. And if you're going to input our x as 0, 3 to the power of 0 is 1. 3 to the power of 2 is 9. 3 to the power of 1 is 3. So then you draw this upon this, and make sure you label your graph. So this is your x, that's your y. And you know that for this, there's an asymptote, a horizontal asymptote of y is equal to 0, because your graph will never cross this. So if you were to plot this, this would -2 to 0.11 would be somewhere around there, and 0 to 1, 2, well 9 is not here, but it'll be like somewhere up there, and 1 to 3. So your function would go something like this. And remember, it's never going to cross this line, so just put an arrow but make sure it doesn't cross that. And then this would be somewhere high up. It'd be going something like that. Now if you want to sketch the inverse, all you have to do is flip these points around. So in order to sketch x is equal to 3 to the power of y, just flip each coordinate around. So put 0.11 here, put 1 there, put 9, put 3. And then instead of putting this back there, yeah, put the x coordinate as the y coordinate. So 0.11 corresponds with -2, right? So you put -2. Well, this is also equal to 1 over 9 because both values are the same. This is just a fraction form. And put the x coordinate 0 as your y, put your 2 as your y, and then put your 1 as your y. So now you just plot this. So 0.11 is somewhere like there. And then 1 to 0. Oops, mistake made. Sorry. 0.11 goes to -2, right? Because that's the coordinate. And then 9 corresponds with 2, so there's no 9 here, so don't worry about that. And 3 corresponds with 1. So our graph is going to go something like this. And remember, there's an asymptote, a vertical asymptote for the inverses, because no number that you input as your y can make x equals 0. So your graph, your inverse graph, will never cross the x equals 0 mark. So I'm going to draw an arrow here, but the vertical, yeah, it's vertical, right? Where's that? Yeah, vertical. The vertical asymptote is x is equal to 0, because the inverse function will never cross 0. So your graph is going to go something like this. And you know the reflections of each other, because if you were to draw y is equal to x on this, so the function y is equal to x would be like that, like that, like that. Y is equal to x, so this is y is equal to x, right? So if you put -1 as your x, your output is -1, 2, that's 2, 3, 3, etc. So if you were to look at them, this graph reflects upon that graph, and that graph reflects upon that graph. And yeah, that's it. So in order to determine which of the following is an exponential function, you have to find the ratio between the bottom number and the top number, the bottom number and the top number, and the bottom number and the top number. So if you were to test that with your calculator, 32 divided by 18, so this would be 1.778. And if you were to do 18 divided by 8, this would be 2.25. If you do 8 divided by 2, well, that's 4. So since these do not have a common ratio, that means this is not an exponential function. Therefore, this isn't an exponential function, because an exponential function normally would have a common ratio, meaning they could be multiplied the same number, and they would, if you were to divide the numbers, you would get the same number, but these are all different. And for this one, if you were to do 625 divided by 125, 625 divided by 125, you get 5. If you do 125 divided by 5, you get 5. If you do 25 divided by 5, it's 5. So since the common ratio, meaning the common multiple, with when you partner them with each of their corresponding values, you get 5, which means your base would be 5, and then just put x equals y. All right, so since the common ratio is 5, if you input any x into here, you'll get the same output as this. So let's just say we put in 3 as our input. 5 to the power of 3 is 125, right? And that's exactly what you get. So that means, therefore, this is an exponential function. All right, example 3. The atmospheric pressure on a balloon or plane decreases with increasing height. This pressure is measured in millimeters of mercury and is related to the distance in kilometers, which is represented by h, above sea level by the formula P is equal to 760 times 2.5 to the power of 0.145 negative times height. So for A, it says, what is the pressure when h is equal to 0? So at 0 kilometers, right? So these are your key things you have to know, measured in millimeters of mercury, this pressure. Yeah, and the formula, you should know that. So at sea level, when h is equal to 0, which you just plug in, what is the pressure? So you just do 0.145 negative times 0, it equals 0. 2.5 to the power of 0 is 1. So 760 times 1 is just 760 millimeters of mercury. Now for II, it says, what is the pressure at 500 meters? Now you have to convert that to kilometers by dividing 500 by 1,000, because the question says that h is represented by kilometers. So P is equal to 760 over 2.5 negative 0.145 times 0.5. Now P would be equal to 760, 2.5. So to find what the exponent is, you do 0.145 negative times 0.5, which is equal to negative 0.0725. And then you just exponent that, so 2.5 to the power of 0.0725 negative equals to P is equal to 760 times 0.935727405. And you times that by 760, right? And then you get P is equal to 711.1528284 millimeters of mercury. Now, since our initial answer is rounded to a whole number, we'll round this to 711 millimeters of mercury. And then, so for B, you graph the function, and you have to determine if it's exponential or not. So in order to graph the function, I chose to label, you have to label your graph. So the bottom side is your height, because that's your input, H. And then your output is the atmospheric pressure, which is, I wrote here, and it's represented by P and millimeters of mercury. So yeah, you have to label that. And then I just chose to scale my graph as 0, 100, 200. So it's each increasing with a 100 interval. And my height, it just goes from 0, 1, 2, 3, 4, 5, 6, etc. So the points I'm going to just use for convenience sake is 0, 2, 4, and 6. So we know that when we input our H as 0, our output is 760 millimeters of mercury. And if you were to input 2 into H, so if I input 2 as my H, so basically you have to do 2.5 to the power of 0.145 negative times 2, which equals that, times that by 760, and it equals 582.65, but we're going to round that to 583. And now if we input 4 into our H, you have to do 2.5 to the power of 0.145 negative times 4, which equals that, times that by 760, and you get 446.69, and we'll just round that to 447. All right, for our final coordinate, if we make our H equals 6 kilometers, once again 2.5 to the power of 0.145 negative times 6, which equals that, times that by 760, and you get 342.45, and we'll just round that to 342, because we're rounding it down to whole numbers like everything else we've done. And since this is 0.4, we round it down to 342 millimeters of mercury. And now you just plot these points onto the graph. So 0 to 760 is like around there. And then 2 to 583, which is somewhere around here. 4 to 447 is somewhere around here. And then 6 to 342 is somewhere around there. So we're just guessing. And if we were to draw that, all right, that's a bad guess. Put that there, because we wanted a decreasing function, right? So yeah. So our graph will go down somewhere along the lines of that. And the reason why we can't have our H as a negative number is because you can't have a negative distance, because that's not legit and isn't a thing. So the final part of the question was, does it seem exponential or not? So therefore, this is an exponential function because, well, there is an exponent, so it is an exponential function because there is an exponent and there is also a base, and the base is 2.5, and there is a base of 2.5. So to combine what I just said, the reason it is an exponential function is because in an exponential function, the form is y is equal to b to the power of x, right? So our b here, which is our base, is 2.5, and our x, which is our exponent, is 0.145h. And the final part of the question is determine the average rate of change from sea level to 500 meters. So it says P at 500 meters, right? but remember that our P was at 0.5 kilometers because we have to convert that. So P at 0.5 kilometers, and right, 0.5 minus 0. And we found these two, the atmospheric pressure at 0.5 kilometers and 0 in our previous question. So we simply have to write our givens, which are 111.1528284 minus 760, because when our input is 0.5 kilometers, we got this. And when we input 0, we got this. And the reason why we use this very large number instead of the one that we simplified is because we want the most accurate answer possible. So we're going to be using this and that. And then 0.5 minus 0 is just 0.5. So if you were to punch this into your calculator, it would be 711.1528284 minus 760, which equals that, divided by 0.5. It would equal negative 97.69433432 millimeters of mercury per kilometer. And if we were to round this, since we're rounding our stuff to whole numbers, the answer would just be negative 98 millimeters of mercury per kilometer. And the reason why is the average rate of change. The bottom values here are kilometers, right? And this top here is our millimeters of mercury. So our units would be millimeters of mercury per kilometer. And it's negative because, as you can see here, it's a decreasing function, right? So that would mean our average rate of change is going down, down, down. So therefore it's decreasing. And that's the reason behind the negative. So this ends the unit. Have fun with miscellaneous course.